I'm happy to introduce Joel Villatoro, who will talk about homotopy theory and algebraic geometry of sheaves of Lie-Rinehart structures.
Hi, thank you very much for the invitation to speak here. I'd also really like to thank Nikita and Anastasia for organizing this really amazing event, and for how beautiful the website is. I'm just like super impressed by like the design aesthetics of this conference, which are really superb. I mean, this is like world class. So thanks for a lot for that. Okay, so what am I going to talk about? Because I'm not 100% sure everybody is super familiar with Lie-Rinehart structures, what I'm going to try to do is go pretty fast through a lot of definitions of things involving Lie-Rinehart structures, just so that I can get to the point I want to make. But if you get confused at some point and you forget, I shared the slides so you can look at the definitions on your own time. When I say algebraic geometry in this talk, I do mean kind of baby algebraic geometry. I'm not going to be proving any grand conjectures or anything, but I'm going to say, I'm going to sort of make the argument that algebraic geometry with Lie-Rinehart structures is like possible and potentially very interesting. And then also similarly for homotopy theory, I'll show how you can do some interesting baby homotopy theory type stuff. So let's get started. All right, so the outline is, first I'm going to look at the big picture. The first half is 1 through 4. I'm going to look at the big picture, and then I'm going to define a lot of things like objects and morphisms. And it turns out Lie-Rinehart structures have a lot of different kind of interesting notions of morphisms and interesting behaviors. And then I'm going to talk about like what happens when you take the sheaf version of all of these things. And then I'm going to explain what I've shown about these things so far. Like what are some things that I've proven. Okay, so very briefly, I got my PhD at University of Illinois with Rui Fernandez, and my general interest is things like Lie groupoids and algebroids and foliations and sort of category theory. And so this is kind of how I ended up here, because a lot of what I'm interested in is kind of combining differential geometry with sort of algebraic geometry reasoning and category theoretic kind of points of view. So this is kind of a natural direction for my research to start to slowly lean in, but I feel like this is kind of where I've ended up. So let's see a conceptual map here. Okay, we have first Lie algebroids. What are Lie algebroids, right? They're like things that sit on top of manifolds that replace the tangent bundle. And then you have these Lie-Rinehart pairs. And how are they related? Well, if you take the sections of a Lie algebroid, you get Lie-Rinehart pairs, right? And on the Lie algebroid bucket, you have things like cohomology, singular foliations, you have homotopy groups, fundamental groupoids. And for some of those things, we have the corresponding stuff for Lie-Rinehart pairs. So we have cohomology for Lie-Rinehart pairs. We have the subalgebras of derivations are kind of the analog of singular foliations. And then, there's obviously more to these theories than what I've put in 4 bullet points, but you get the idea. Going the other way, you have something, so this is maybe less well known or less obvious. There's a spectrum operation. But the one problem is that it's not exactly clear that if you take the spectrum of something, then you end up with a Lie algebroid, right? So this is something that just happens naturally in algebraic geometry, right? The spectrum of a ring is not a manifold; it's something else, and the spectrum of a module is not necessarily a vector bundle. It's going to be a sheaf. So in order to make sense of a little bit more of this, we have to put a big box around Lie-Rinehart structures, and we're going around Lie algebroids. We'll call Lie-Rinehart structures, which are the sheaf version of Lie algebroids. Okay. So just quickly, I have some slides of like interesting reading about these topics. I don't think I have the time to really explain everything that's in these papers, but these are just some of the papers I've been looking at to try to understand these things. And also singular subalgebroids, Marco Zempelin is a very interesting paper. Okay. So objects and morphisms. What's a Lie algebroid? A Lie algebroid is a vector bundle, right? So probably everybody knows this. It's a vector bundle where you have a Lie bracket on the sections, and you have a Lie algebra homomorphism from the sections to vector fields. And you have a sort of Leibniz type rule for, it has a derivation property with respect to scalar or to multiplication by smooth functions. Now, this is pretty interesting. If you want to know what a Lie-Rinehart pair is, well, all you have to do is you have to take this definition of the algebroid and you have to replace M with a ring, right? You think of that ring as like the smooth functions on M, and you replace A with a module for that ring, right? So a Lie-Rinehart pair is, we'll call it A and R, and R here is a commutative unital algebra, and A is an R module, right? And it has to have the following information. It has to have a Lie bracket on A, and it has to have a module homomorphism from A to the derivations. And then these two things have to be compatible. One of the compatibility conditions is that rho has to be a Lie algebra homomorphism. And then the other compatibility condition is there's a Leibniz rule, right? That it's the exact same formula for the Lie algebroid. Now, what are some examples of Lie-Rinehart pairs? So I just told you that examples of Lie-Rinehart pairs come from sections of an algebroid. Let me give you some examples that aren't that necessarily. So if you have any commutative unital algebra, then you can take the module of derivations, and that's a Lie-Rinehart pair, right? Here's a more complicated example. Suppose you have a differential graded algebra for people who are interested in that kind of thing, and assume that it's basically generated freely in degree 1, which basically means that all of the degrees above 1 are just wedge products of the degree 1 over the degree 0 part, which, because it's a differential graded algebra, is actually commutative algebra. So these are graded commutative algebras. And if you take basically the dualization of this object, so there should be a parentheses there, but it's fine. If you take the dualization of this object, you can define derivations on that using this formula here, and you can define the bracket using this formula here. So you can take a look at that formula in the slides if you want to examine it more closely, and you end up with a Lie-Rinehart pair. Now, as a cute exercise for people probably who do algebraic geometry, this is a really easy exercise. For people who aren't familiar, maybe it's kind of a little bit trickier, but you can prove that bullet point 1 is an example of bullet point 2. So that bullet point 1 actually comes from such a differential graded algebra. Now, if you have a Lie algebroid and you have an open set, of course, like I said, you can take the sections where you just look at what are all the smooth functions over a given open set, and what are all the sections over a given open set. Here's another example that's not necessarily a Lie algebroid. If you have a sheaf of Lie subalgebras of a Lie algebroid, right? You start with a Lie algebroid, and then you take some sort of subsheaf of the sections that's closed under the action of C infinity of M. So it's also a submodule. Then you get a Lie-Rinehart pair. And that is what is called by many people a singular subalgebroid. And probably the most famous examples of these are singular foliations, which have some people studying them as well. Now, what are some useful constructions with Lie-Rinehart pairs? Okay, so one useful construction is the notion of an action. Now, if you have a Lie-Rinehart pair, an action corresponds to a homomorphism from some like ring, from your base ring to some other ring, and a Lie algebra homomorphism that makes this diagram commute. But you should think of this as kind of like the analog of a Lie algebra action on a ring. And what happens is you can show that if you take the tensor product of S with A, and then you take the pair, that makes it an S module, and then you combine it with S, then you get an action Lie-Rinehart pair. I'm not explaining how to define the bracket on S tensor R, or sorry, S tensor A, but that's an exercise if you like using this data. But if you're familiar with the construction of an action Lie algebroid, I encourage you to try to check that this is actually also that an action Lie algebroid is actually an example of this kind when you pass to sections. And if you have a Lie-Rinehart, so if you have a Lie-Rinehart pair and a homomorphism from your ring, from your base ring to another one, actually, is that going the wrong way? No, it's okay. if you have a Lie-Rinehart pair and oh, it's going the wrong way, sorry. This should be phi from, sorry, this should be phi from R to S. It's easy to get these things mixed up. If you have such a homomorphism, then you can do something that's kind of like a base change, where you take a fiber product over this tensor product, which you should think of as kind of like if you're like, from the point of view of vector bundles, this actually is basically like, this is like the phi is like a smooth map, right? And this is like the pullback operation going from R to S. And this thing here is basically the pullback bundle, right? So what you're doing is you're taking the fiber product of the pullback bundle with the derivations on your new manifold, and you get something here, right? And this fiber product exists because these are just purely algebraic objects that you can construct no problem. And this thing is canonically a Lie-Rinehart pair, which we'll call the base change. Now, let's see. So now we know about Lie-Rinehart pairs. We know some interesting constructions. How do we define morphisms? Well, there is one really simple way of defining a morphism, right? So if you have two Lie-Rinehart pairs, you could just ask for a homomorphism of the base rings and a homomorphism of the associated modules that's sort of compatible with the actions. That is, makes some diagram including involving the anchor maps commute. Now, this thing here is kind of funny, right? But how do you define this map? You know that this B comes with a map to derivations of S. And because you have this homomorphism, you can use a composition operation to go from derivations on S to derivations that start in R and then end in S, right? And then here you have a map from A to derivations of R. And this is really the only sensible diagram that you can draw that you would expect to commute with the anchor maps. So like if you really sit down and think about how do you come up with a diagram involving anchor maps that would make things work properly, this is really the only one you'll come up with. And then of course, what we want is that F is a Lie algebra homomorphism. So this is like, you should think of this as compatibility with the anchor, and this is compatibility with the bracket. And so we'll call the category that you get from defining morphisms of Lie-Rinehart pairs LRP. Okay. So what are some examples? Suppose you have a Poisson map, right? So this is very relevant to this conference. If you have a Poisson map, if you take as your ring homomorphism the pullback map for your smooth map, and as your algebra homomorphism your pullback of one forms along differentials, then what you will get here is a morphism of Lie-Rinehart pairs exactly in this way. Now, if you have, here's another example. If you have a Lie algebroid, we can take sections to come up with Lie-Rinehart pairs associated to open sets. And if we look at the restriction of, say, from one larger open set to a smaller open set, this is also a morphism of Lie-Rinehart pairs. So the restriction maps. Here's some weirdness. If you have a homomorphism, we already know that there's canonically a Lie-Rinehart pair associated to both R and S. But in general, there's not a homomorphism of those Lie-Rinehart pairs. Now, I mean, if you think about this long enough, you might think, okay, that, like it seems like it should happen. If you're like going at it totally naively, and then the more you think about it, the more you think it's completely unreasonable to expect this to happen. But the point is basically that this derivation operation, right, the thing that sends R to dir R is not a functor. And so one interesting question that I don't really know the answer to is there a nice subcategory of commutative unital algebras for which this derivation actually is a functor? So for which there's like a canonical map of their derivations like this. And I suspect that the answer to this is something like Ital. But I won't go into it too much. All right, so non-example, Lie algebroid homomorphisms. Lie algebroid homomorphisms are not morphisms of Lie-Rinehart pairs. So this is kind of weird, right? Because Lie algebroid homomorphisms are the things that you usually study when studying Lie algebroids. So that means that we have some work to do. Now, what are some, sorry, one last thing. There's a theorem by Higgins and Mackenzie they proved back in 1993 that every Lie-Rinehart morphism actually factors through an action Lie-Rinehart pair. So there's like a nice factorization theorem that you can prove about these kinds of morphisms. So how do we fix this problem, right, that we have not captured Lie algebroid homomorphisms in our definition of morphism? Well, you go to what's called a comorphism. Why is it called a comorphism? We call it a comorphism because the map at the level of rings goes in the opposite direction as the map at the level of the algebras, right? So now the map of rings goes from S to R, right? R is always associated to A and S is always associated to B. And well, in order to define a homomorphism of modules, you need to take a tensor product of B with R in order to really make sense of this map. So that's what you do. And then you ask for a diagram to commute, right? And then I encourage you to figure out what are the maps in this diagram. They're all very natural. They're really the only ones you can come up with. But basically on this side, you can see that if you have an element of this is like a sum of elements of R tensored with elements of B. Each one of these elements of B gives you a derivation on S. By composing it with a homomorphism, you get a bunch of elements of R, and then you multiply them with elements of R to get an element of R. I said that very quickly, but it's something like that. And then this is the annoying thing about comorphisms is they have a kind of ugly definition for compatibility with Lie bracket. But if you're familiar with the definition for compatibility with Lie bracket for Lie algebroids, this formula probably looks really familiar to you. So that tells you that we're on the right track. Of course, I don't have enough time to explain every part of this whole formula, but it is fairly natural when you think about it for long enough. And so the category of Lie-Rinehart pairs with comorphisms we'll call LRP-co. So what are some examples? So Lie algebroid homomorphisms. Here's another weird thing. If you have a homomorphism of Lie-Rinehart pairs, you still don't get a functor to the category of Lie-Rinehart pairs with comorphisms. And this is even weirder because because if you assume that these rings come from manifolds, then you do get such a functor, or you do get such a functor. So I'm really interested to know if somebody can come up with a nice category of rings that's a pretty algebraic and kind of classical class of rings for which you have a nice functor into the category of Lie-Rinehart pairs with comorphisms. That would be very interesting to me. And if you have a Lie-Rinehart pair, you always get, if you have like a base change, then you always get a comorphism from the base change to the original thing again. And then this is a theorem. I don't know if this appears anywhere in the literature earlier. If somebody knows, please let me know. So that's why I put a question mark on the V here, because I'm not sure if somebody else has proved this, but it turns out that every Lie-Rinehart comorphism factors through a base change. And if you're familiar with Lie algebroids, you might think, sometimes if the base map for Lie algebroid is nice enough, the Lie algebroid homomorphism factors through the pullback algebroid. And this is basically saying that, well, because we're in the algebraic category, the pullback algebroid is always fine, right? It never doesn't exist. And so this factorization theorem is true. But in the category of Lie algebroids, this is false. So this is kind of a nice property that the algebraic universe has that the smooth universe does not. So let's quickly get onto sheaves, right? So what's a pre-Lie-Rinehart structure? It's a functor from the open sets to Lie-Rinehart pairs. What is a Lie-Rinehart structure? A Lie-Rinehart structure is one for which this functor is, it satisfies the usual sheaf axioms, right? And then we use this notation, this little squiggly arrow, A squiggly arrow X. This is suggestive of the fact that A is sort of like a vector bundle over X, right? You think of A as sort of like a vector bundle over X, but because it's a sheaf, it's not really a vector bundle. So I don't want to use a regular arrow because this is not like a set. This is a sheaf. Okay. And then the ring of functions is OX and the module is A. Okay. So examples, take a Lie algebroid. if you have a Lie-Rinehart pair, you can define the spectrum of your Lie-Rinehart pair, basically. So as the base map, the base topological space, you take the spectrum, and then lemma, there's a usual procedure for constructing from a module a sheaf of modules over the spectrum. And lemma says that if you actually go through this process, you'll see that it results in a well-defined Lie-Rinehart structure. So it makes sense to talk about Lie-Rinehart structures on, say, a scheme, which are locally the spectrum. So this is kind of like saying it makes sense to talk about like quasi-coherent Lie-Rinehart structures or coherent Lie-Rinehart structures.
Joel, there's a 5-minute warning.
Okay, thank you. Now, morphisms and comorphisms all make sense in the sheaf setting. This is where like the notation starts to get kind of annoying, because already morphisms and comorphisms for Lie-Rinehart pairs are kind of complicated. You have to take tensor products and write down some complicated looking formulas. So, but you can make sense of this, right? A morphism is basically a triple where you have a map at the level of topological spaces, you have a map at the level of the rings of functions, or the sheaf of rings on the Earth space, and you have a morphism of sheaves, right? Going from A to B that's compatible with the module structures. And we say it's a morphism if it's locally a comorphism. So this is something that's kind of annoying. So when you define a morphism of Lie-Rinehart structures, so in the sheaf universe, a morphism corresponds to a comorphism in the algebraic, in the like local geometry algebraic universe. This is an unfortunate fact, but we call this a morphism because here you see that we go from A to B, and at the level of the spaces, we go from X to Y. So those two arrows go in the same direction. So that's why we say it's a morphism rather than a comorphism. Now, we can also define comorphisms in basically the exact same way. But we call it a comorphism because the map at the level of spaces goes the opposite direction. And then we say it's locally a Lie-Rinehart morphism. What are the main results? Okay, I'm almost done. Now, Lie-Rinehart structures on manifolds, if you assume that the ground field is the real numbers, which I haven't needed so far, right? You can talk about Lie-Rinehart structures on manifolds. And when I talk about Lie-Rinehart structure on manifold, I always assume the sheaf of rings is something like the ring of smooth functions, or the ring of analytic functions, or the ring of holomorphic functions on a complex manifold, okay? So we never do any other kinds of sheaf of rings. So the ring part of the pairs is always the sort of usual ring of functions. And you can define homotopies by using this notion of morphism we've defined for Lie-Rinehart structures, right? So morphism is like, a homotopy is like where you take something from A to the interval 0, 1 to B, and then you add some boundary conditions. And you can define fundamental groups by taking pointed homotopy classes of such morphisms. And you can define even a fundamental groupoid, right, by taking homotopy classes from the interval into your Lie-Rinehart structure. So here's one theorem. Each one of these homotopy groups is indeed a group, and this groupoid is indeed a groupoid, right? This is just a purely set theoretic claim for now, right? So main results. There's a nice class of Lie-Rinehart structures which are called Frobenius integrable, okay? And the first main theorem basically says that if you have a Frobenius integral Lie-Rinehart structure, then you have a partition of the manifold into leaves. Now remember, this is not like Lie algebroid. This is really something abstract. It's like a sheaf of Lie algebras on your manifold. And I'm saying you start with a sheaf of Lie algebras on your manifold with like an anchor map and a bracket, and you actually get a partition into smooth manifolds, right? And then the other theorem, this is the theorem that sort of says that homotopy theory should work for this setting. That if you have a fibration of Lie-Rinehart structures, which have this property of being Frobenius integrable, then you actually get a long exact sequence in homotopy. So that's actually quite nice. And this is an extension of another result for Lie algebroids by Braik and Zhu. So in the second part, what I'm going to talk about is more details on the definition of Frobenius integrable, which is really important for the theorems. Some examples of Frobenius integrable. I'll sketch a proof of one of the theorems, and then I'll speculate wildly about properties of the fundamental groupoid of a Lie-Rinehart structure. All right. Thank you very much.
Okay, thank you, Joel. Let's thank Joel. Very nice talk. Thank you very much. As before, I encourage everyone to go to Joel's parallel session to ask questions, or you can send them through Slack or chat. Okay, so our next speaker is Jan. So Jan, would you like to start sharing your screen? So I'm going to make you a co-host now. So again, we'll wait a few minutes until exactly on the hour, just in case someone wants to tune in exactly for your talk.
Yeah, sure. I'll share the screen.
Yeah.
Great.
And now we cannot see the camera.
Well, we see the camera.
Oh, you also see me. So
we also see
okay.
us.
Yes.
Okay, good. So it's not, or maybe now it will stop.
Yeah, now
yes.
it's stopped. Yeah.
Now it's stopped.
Okay, so I don't know how to. So I can connect also with the computer, but then like it will be just another participant, I guess, or maybe.
That's okay. That's okay. You can do
that's
that.
completely fine.
If you want to look also at me.
Yeah, we do.
Yeah, maybe it's still better than the slides.
Yes, that's right. Maybe. That very well may be.
Okay, so you should also.
Okay, so yes. So I can see the two. So which microphone are you using? The microphone from your iPad or your laptop? Okay.
Okay.
Okay, good.
Then yeah, make sure to keep laptop muted.
Yeah. So the only problem is with your laptop video, it's very dark.
Wait.
Yeah, that's a little better. Yeah, it's not that big of a deal, but
I can try to do something.
Only if it's not too much trouble. I mean.
No, I think it's fine. Yeah, this should be.
Okay. So whilst Jan is setting it up, I just want to make a little remark that so even though everyone's microphones are necessarily muted for the plenary session, we still encourage you to turn your cameras on, just because especially for the speaker, it makes a kind of more lively event when you have this visual feedback. So and you know, if your internet connection isn't so great that you're afraid that having all these videos on would drag your internet, you can always kind of just collapse most of the videos. And if you have them collapsed, then they're not streamed to your machine, so it shouldn't drag on your connection. Right. Okay, so let's just wait a few more seconds.
Okay. I think it's time. So I'm happy to introduce Jan Poelman from University of Geneva, who will talk about quantized modular spaces of flat connections and triangulations.
Oh, thank you very much. And also thank you very much for giving me this slot and also for organizing such a nice conference. And I will be talking about what will hopefully be my thesis. And this is done under the watchful eye of Pavel Severa. So the title is Quantized Modular Spaces of Flat Connections and Triangulations. So the first part is old story, this quantized modular spaces of flat connections, and this triangulation that is the new addition. And the kind of modular spaces we consider are modular spaces of flat G connections for a Lie group G on surfaces. So this is the setup, and you probably know that such structures are abundant, and they have there are many important examples of them. Partly because these moduli spaces of flat connections on surfaces, they are symplectic or Poisson or something I will use, a quasi-Poisson manifolds, or if they are manifolds, then they are Poisson manifolds. This is the famous Atiyah-Bolt structure, symplectic structure, and generalizations of that. And okay, sorry, I wanted to see all of you. And there is a natural question to how to quantize these structures. And this was done by Pavel Severa and David LeBlanc. And they have a procedure that gives you algebras that quantize these Poisson structures, but they are algebras in some kind of bit different category, which you craft using the Drinfeld associator. And the question in this procedure, it involves cutting up the surface into small parts and then gluing it back together. And there are lots of choices you can make while cutting up the surface. And this is the answer we will provide, is how does the quantization depend on these choices? Okay. And I will try to give you all the necessary background to follow. So first, let me just talk about modular spaces of flat connections. So for me, G is just a connected Lie group, and sigma will be a surface with a non-empty boundary. I will always consider non-empty boundaries. And then one can look at this space I will call M sigma of G. Okay, and this is the space of all flat connections on the trivial bundle on G. So because the surface has non-trivial boundary, all the principal bundles are trivial. So at least So we look at just flat connections on this trivial bundle, and we take them up to gauge transformations. So gauge transformations, these are, here we can just see them as functions from the surface to the group. And if you have a connection, there's a Lie algebra valued one form on sigma, you can change it by this small formula here. Okay. And there is an equivalent description of this space, which I think when people say character variety, they rather mean this one, but these two are the same. And so this other description is just, you look at homomorphisms, or group homomorphisms from the fundamental group of the surface to your group G. You choose a base point, and then you mod out by G. So let me maybe write, how does the G act? So if you have a homomorphism phi gamma, then if you act on this homomorphism by G, what you get is phi gamma, and it's conjugated. So the action is simultaneous conjugation by all the simultaneous conjugation of all the maps. So Nikita has but I think here this is the smooth category, and so okay. And this isomorphism between these two pictures is very easy. You just, for any flat connection A, you can take holonomy along path. And because we only look at gauge transformation at flat connections up to gauge transformations. Then this holonomy is only defined up to conjugation at this at this marked point, right? Because there is still, you can still use some gauge transformation. Okay, and what I will consider is a slight